Okay, let's just dive right into this explainer. You know that feeling when your phone shows full bars, but your data is just completely dead? Or when a call just drops out of absolutely nowhere? Well, today, we're essentially riding shotgun together to see how telecom engineers actually diagnose network health out in the real world. We're going to do this by looking under the hood of a pretty incredible piece of industry software called TEMS Investigation.
But before we get buried in the raw data, we kind of have to ask a basic question. How do we take that universal frustration of a dropped call and turn it into something visible, something actionable? I mean, we can't literally see radio waves, right? But by using these specialized drive testing tools, engineers can translate those invisible frequencies and interference into structured data that tells a really specific story about what's going on in the 3G network.
So, here's our roadmap for today. 1. The drive tester's dashboard. 2. Meet the cell types. 3. Decoding radio parameters. 4. HSPDA, speed and quality. And finally, 5. Tracking the events window.
All right, Section 1, the drive tester's dashboard. Picture this. You're a trainee, sitting in the passenger seat of a drive test vehicle, zooming down the highway. Your laptop's open, and your main goal is to look at these TEMS software windows and diagnose the network's health in real time. You aren't just staring at a wall of numbers here. You're translating highly abstract 3G radio parameters into actionable insights. You're hunting for exactly where the network is failing the subscriber, and more importantly, why it's failing.
Moving right along to Section 2, meet the cell types.
Now, it's actually super fascinating how the system defines the different characters, basically the cell towers, that are constantly fighting for your phone's attention. First up, we have the SC, or serving cell. This one handles your phone when it's just chilling in idle mode. But the second you switch to dedicated mode, like you're actually making a call or downloading a file, you rely on the AS, the active set. Think of the active set as the absolute VIPs of the network. These are the specific cells actively providing your current connection. But the active set isn't out there alone. We also have neighbors. The MN, or monitoring neighbor, is pretty much exactly what it sounds like. These are the cells the network knows about, it's monitoring them, and they are standing by ready to hand your call over to if your current signal starts to fade. And then we have the DN, the detected neighbor. These are cells your phone can hear shouting from way off in the distance, but they aren't officially on the approved list to handle your connection.
When you're looking at the TEM's user interface, specifically the WCDMA serving, active set, and neighbors window, you can actually watch these cell types working in real time. You've got your active set rows right at the top managing the connection, and then the monitoring neighbor rows sitting right below them, just waiting to take over as the car drives into a new coverage area.
The absolutely crucial takeaway here is the difference between those monitoring neighbors and detected neighbors. An MN is pre-approved. The system knows it exists and can seamlessly hand your call over to it. A DN, though, no way. It cannot be handed over to. It's essentially a really loud voice outside the VIP club that the bouncer refuses to recognize. And because the network can't hand your call over to a DN, a strong DN signal actually just acts as severe, massive interference to your current call.
And this brings us to a classic missing neighbor problem. Imagine a detected neighbor sitting at the bottom of your screen with a super strong signal. It's incredibly loud. But since it isn't defined as a monitoring neighbor, it's not allowed in your active set. So it's literally just creating noise, which completely tanks your signal quality. This right here is one of the main reasons calls drop even when your phone is proudly displaying full bars.
Let's jump into Section 3, decoding 3G radio parameters.
To actually make sense of all the data flying across the screen, the very first thing we need to do is identify our frequencies. We do this using a parameter called UAFRCN, which stands for UTRA Absolute Radio Frequency Channel Number. Yeah, I know, it's a total mouthful, but all it really does is identify the exact frequency channel being used in the UMTS bands. It tells the engineer exactly which tiny slice of the radio spectrum they're looking at.
Okay, once we know our frequency, we need to know the power. For that, we look at the Received Signal Code Power, or RSCP. In drive testing, we rely heavily on color coding to spot issues fast. An excellent signal is going to sit somewhere between -10 and -65 dBm. But if you're watching the software and you see a value drop below -95 dBm and suddenly light up bright red, you instantly know you've hit a bad coverage spot. But here's the catch. Power isn't everything. Quality is just as critical. That's where EC/No comes into play. This measures the received energy per chip against the noise ratio, so basically your signal quality. Again, the colors tell the story. Excellent quality sits between 0 and -8. But anything slipping past -14 turns red and is flagged as very bad. If you have a bad EC/no but a good RSCP, it means you've got strong coverage but terrible interference.
All right, Section 4, HSDPA, Speed and Quality.
If you've ever sat there wondering why your data is lagging or a video is just endlessly buffering even though you have full signal bars, well, the answer usually lies in something called the Channel Quality Index, or CQI. CQI is basically the bridge between those raw radio waves and your actual download speeds.
By pulling up the HSDPA analysis window right next to the DU meter in the software, you can see this relationship happening live. The HSDPA window shows the CQI value that the phone is reporting, which reflects the real radio conditions. Right next to it, the DU meter tracks the actual data throughput. This setup lets engineers see, in real time, how invisible radio conditions directly throttle or boost the actual megabits per second that a subscriber gets to experience.
This matrix we're looking at is basically a drive tester's ultimate cheat sheet. It maps the direct relationship between the Channel Quality Index and what we call the subscriber feeling. A high CQI, anything above 15, translates to a good subscriber feeling, pushing throughput speeds over 1.39 megabits per second on the standard 3G network. On the flip side, if your CQI drops below 9 because of interference, it guarantees a pretty miserable user experience, capping speeds way down under 320 kilobits per second. Finally, let's wrap up with Section 5, Tracking the Events window. Tracking signal strength and speed is awesome, for sure, but we also need to see the actual conversation happening between the mobile phone and the network. The events window captures the chronological story of the call by logging all the critical Layer 3 messages. We're talking call attempts, call established, successful handovers, and of course, the dreaded dropped calls or blocked calls.
Watching the events log lets an engineer play detective. You can pinpoint the exact millisecond a call was established or track the exact sequence of handovers. What's kind of mind-blowing is that these handshakes are happening at lightning speed, literally fractions of a millisecond, while the car is just cruising down the street. If a call drops, this window tells you exactly when the connection died, letting you cross-reference that exact moment with the radio parameters. So you can see, for example, a sudden massive spike in interference from a missing neighbor right when the call failed.
When we piece it all together, the software gives us the complete chronological life cycle of a typical mobile session. It starts with the call setup, moves into call established, handles the handovers as the user travels, and finally wraps up with a call end. Whether that end is just a normal user-initiated hang-up or a sudden drop caused by pilot pollution, the drive tester now has the hard data they need to report the failure and actually get it fixed. Well, we've definitely covered a lot of ground today. Now that you have the tools to translate a wall of abstract parameters into a crystal clear, actionable picture of network health, you aren't just staring at a screen anymore. You're actively mapping the invisible grid that connects us all. So, armed with all this knowledge, what network problem are you going to solve next? Thank you so much for joining me for this explainer, and I will catch you in the next one.